Ladies and gentlemen, buckle up. It's gonna get a little complicated, and this might be kind of a long video because I got a lot to say about this. Last time we left off explaining the Bayesian philosophy of populations, and the basic idea is you take your best guess of what the population values are, you gather data and combine that with your prior belief to compute a new estimate of what the population might look like, and then you repeat that iteratively, knowing that you can never really capture the entire population completely. So the frequentists or the likelihoodists or whatever you want to call them, they have a different philosophy. But first, in order to understand that, you need to understand the central limit theorem.
The central limit theorem is the foundation of all of likelihood and frequentist statistics.
And if the central limit theorem weren't true, guess what? The entire field of statistics as we know it would crumble to the earth. No exaggeration, like if the central limit theorem weren't true, most of the statistics we do would crumble and fall to ruins.
Wouldn't mind that at all, man. Stats is dumb.
What'd you say? Nothing. That's what I thought. So first, I want you to consider an experiment. Let's say that you had a dice and you had nothing better to do but to roll that dice. So you roll that dice and then you record your results. But you don't do this just once, you do this 100 times, then 1,000 times, then 10,000 times, then 1,000,000 times, then 1,000,000,000 times. Why? Because you love rolling dice. Let's just put it that way. After doing that for a long time, you decide to plot the distribution. Any guesses on how that would look? Oh, if you said this, you are right on the money. So this is what we call a uniform distribution, which means that every single event is equally likely. And why is that? Because the probability of rolling a 1 is the same as the probability of rolling a 6, or a 5, or a 4, or a 3, or a 2. And if you have an unbiased dice, and if you have an unbiased die, I just feel awkward about calling it a die instead of a dice, I don't know why. Then you should see equal probability across the entire distribution. Now let's say, for some odd reason, you decided you want to do the same thing, except a little bit different. This time, instead of rolling 1 die, you roll 5 dice. And then you computed the average of the 5. And let's say you do that 10 times, then 100, then 1,000, then 10,000, then 1,000,000, etc., etc. Now let's say you're to plot this distribution, the distribution of means. Any guesses what it would look like? Now remember, the distribution with just one roll was flat. Any guesses what it would look like now? This is what it looks like. Holy cow, things done changed on us. So what we see here is you have a very small probability of getting a 1 and a very small probability of getting a 5. Let's think about that for a minute. In order to average a 1, you will have to roll 5 ones. That's kind of unlikely. Likewise, with a 6, you would have to roll all 6s, which also is unlikely. So there's only one way to get a 1 and only one way to get a 6. On the other hand, there's lots and lots of ways to get like a 3 or a 4 or a 3.5 and that sort of thing. And so that's why you see this peak in the middle. Now, just for fun, let's say you're just like super excited about this dice game and you decide instead of rolling 5, you want to roll 30. So you gather 30 dice in your hands and you start a-rolling. And then just as before, let's say you computed the mean of 30. Any guesses on what that distribution would look like? Well, here it is. So in this situation, now the probability of getting a 1 is practically 0. Why? Because you have 30 dice. In order to average 1 on 30 dice, all 30 of them have to land on 1. That would be extremely unlikely. What we just demonstrated is called the central limit theorem. And the central limit theorem refers to the distribution of means. Because remember what we did? Let's say it was the 5 dice scenario. We rolled 5 dice and then computed the mean and then plotted the distribution of those means for each of those different rolls. And so there are 3 important facts about the central limit theorem. Number 1, the mean of the means is equal to the means. Say what? The mean of the distribution of means is equal to the population mean. So say it with me.
The mean of the mean is equal to the means. The mean of the mean is equal to the means. The mean of the means is equal to the means.
Or again, the mean of the distribution of means is equal to the population mean. Now what the heck does this mean here? If you were to go back to the distribution where you rolled it just once and compute the average out of all those bajillion rolls that you did, what would the average be? Well, the average would be 3.5. If you had the equal probability of 1 through 6, and you added those values up, 1 plus 2 plus 3 plus blah, 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 and then divided by the number of dice, which in this case is 6, your answer would be 3.5. So the average value of this distribution is 3.5. And so look what's happening on this histogram. The mode of that distribution falls at, you guessed it, 3.5. So that's fact number 1. The mean of the distribution of means always equals the population mean. Number 2, the variance of the distribution of means shrinks as the sample size increases. So let's go ahead and overlay multiple distributions and see what we find. So here is the distribution where n is equal to 1. Here's the distribution where n is equal to 10. Here's the distribution where n is equal to 30. Notice what's happening is that the distribution gets narrower and narrower as you increase the sample size. So that's fact number 2. Fact number 3. The distribution of means will always, always, always be normally distributed regardless of what the underlying distribution is. So you remember at the beginning when we rolled one dice 1 billion times and then looked at the distribution and it was flat or uniform? Every roll had equal probability. Well, when you compute the means and look at the distribution of means, guess what? That distribution ain't normal, folks. So this is actually pretty powerful stuff, because you remember when we said we make the assumption of normality? Well, oftentimes it actually doesn't matter all that much. Why? Because if we're computing a mean, we know that the distribution of those means is actually normal, so the assumption is basically met anyway. So now back to the second point that I made. You remember how I said the larger the sample size, the more your variance shrinks? Well, you might be asking,
Okay, well, how much does it shrink exactly?
I know nobody's probably asking that, but ask it now. Well, it turns out that the variance of the sampling distribution shrinks by a factor of the square root of n. Why? Why square root of n? Don't worry about it. Just trust that some mathematician a long time ago figured that out. So this tells us that sigma divided by the square root of n is actually the standard deviation of the sampling distribution. We call this the standard error. And let me just say that again. The standard error is the standard deviation of the sampling distribution. Or it is the standard deviation of the distribution of means. Or in other words, sigma, which we talked about earlier, is the standard deviation of the raw scores, and sigma divided by the square root of n is the standard deviation of the distribution of the means.
Boy, that was fun and all, but what's the point of all this? I want to know.
Yeah, I know, we're all like talking about likelihood and frequentists and that sort of thing, and now we're talking about rolling dice. What the heck does this have to do with anything? Think about it this way. Let's say you've got a treatment group and a control group, and you compute means for each of them. And so let's say the control group had a mean of 5 and the treatment group had a mean of 6. But think about it this way. Your experiment is one experiment, but you could think about it as belonging to a distribution of means. All right, who here has seen Groundhog Day? You know that movie with Bill Murray where he lives the same day over and over and over again? If you haven't seen it, you should watch it. Excellent movie. Okay, so in that movie, he's moving the same day over and over again, and every morning the exact same song wakes him up for his alarm. Every day he goes to the same diner and the waitress drops a plate at the exact same time, and people have the exact same conversations. And the only thing that changes are the things that he does differently and people's reaction to what he's doing differently. But statisticians would be like, that ain't the way it happened. Why? Because statisticians believe there's variability. So if you were to repeat this experiment, the treatment and the control group, an infinite number of times, you were to live Groundhog Day over and over and over again, guess what? The second time you did it, the treatment group might have a mean of 6.5 instead of 6, and the control group might have a mean of 5.2. And the day after that, it might be 4.9 and 7.8. And every day there's gonna be a different estimate of those means. And if you were to plot those means, the mean of the treatment group and the mean of the control group, guess what? The distribution of means for the treatment group and the distribution of means for the control group are going to look normal. And its variance will be proportional to the sample size. So what does that tell you? That tells you that the larger your sample size, the more precise you're going to be about the population estimate. Okay, now let's link back to our previous video. You remember how I said, according to a probability density function, if we know the mean and the standard deviation of a population, we know the probability of every single score occurring. And remember how I said previously that we know the standard deviation of this distribution of means? It was a standard deviation divided by the square root of n. We know that on average, the mean of the distribution of mean is equal to the population mean. And if our sample size is relatively large, we know that the mean that we compute in our sample is probably going to be pretty close to the population mean. So we have an estimate of the population mean and we have an estimate of the distribution of means, which again is our standard deviation that we compute in the sample divided by the square root of n. Well, guess what, people? You have a good guess about what that population standard deviation looks like. Now, what does that mean about frequentists versus likelihoodists? Okay, again, both Bayesians and frequentist people want to know what the population looks like. The Bayesians say that the population is always changing, and the best we could do is bring our prior beliefs into it and constantly update our beliefs based on data that we collect. Frequentists don't like that. They say that the population is a single value. Instead, what they say is let's pretend that your experiment is only one experiment, but it is representative of an infinite number of experiments you could have performed. And if that's the case, we can use the central limit theorem to estimate what the population would look like. Now, do you get why they're called frequentists? Because they're thinking about frequent experiments happening over and over and over and over again. And by the way, that is the distinction between a frequentist and a likelihoodist. A frequentist actually does lots and lots and lots of experiments, and the likelihoodist just considers this experiment as if it was one of an infinite number of experiments that could have been done. More or less, though that's an oversimplification. So with that, let's review our learning objectives. Number 1, understand what a standard error is. And again, all that is your computed standard deviation divided by the square root of the sample size. Understand what a sampling distribution is and how it allows us to estimate a mean and a standard error. And again, a sampling distribution is just the distribution of means, and we know that on average, that distribution of means will equal the population mean. And like I said earlier, its standard deviation is the computed standard deviation divided by the square root of the sample size. Understand the difference between a distribution of means and a distribution of raw scores. So relating back to our treatment versus control, the distribution of scores of each single individual is a distribution of raw scores, but when you average those and you perform the experiment multiple times, that is the distribution of means. The 3 important facts of the central limit theorem. Again, the mean of the distribution of means is equal to the population mean. The variance of the distribution of means shrinks as your sample size gets larger, and this distribution of means is always normal regardless of the shape of the underlying distribution. And finally, don't get bogged down in the details, like seriously. This is pretty complicated stuff and very theoretical and that sort of thing, and it's okay. As long as you understand these learning objectives, you're good. So with that, peace out.